I really like to record these. So. What's that? Move the table like all the way over here. Yeah, but then the problem is you get this weird like tilted, like the way that lighting works because the depth of field is gonna be all screwy and you're gonna get this crazy out of focus stuff over here. I think. I have a wide angle lens at home. I'm gonna bring. I just forgot to bring it. So yeah. And then I don't know. People seem to enjoy the fact or appreciate, maybe not enjoy, but at least appreciate the fact that I have my stuff recorded less. Quarter, so I figured I'd do it again. Okay. Right. So this is Math 304. I believe it's Math 304. Yeah, I'm in the right place, I think. Okay. So this is vector analysis. I will point out if you are here and you're going to ask me if you could possibly please be added to the class. I should point out that there are something like 20 people on the wait list for this class. I have no control over how many sections of the class there are. I have no control over permission codes until Friday, and I'm not allowed to go over the fire marshal's limit on the room, which is 35 desks that are in here. So that's sort of what I'm like constraints that I work inside. So it's if you need this, if you want more of it, you gotta talk to the department. I can't do anything about it. You have my sympathy, but there's not much I can do in terms of actual action. So okay. Right, so I'm Brian Tully-Doyle. I joined the math department a couple of years ago, right in the middle of the pandemic. So this was my first year back in the classroom.
Thank you.
Yep. I was a student here, so although I don't remember taking this class, I must have at some point. But it's pretty exciting to be back and to be teaching people. I've been gone for quite a while. I really like teaching math and working with students, and I think that there's a lot of cool stuff in this class because we get to do calculus finally the right way. It's like a year and a half of crud that they taught you about how calculus works, and now we're going to do it the way everybody actually uses it. What's going to happen? We're going to do real calculus. It goes in the language of vectors. So I'm going to talk a little bit about the relationship between this class and Math 241 a little bit further in. I see a couple of people squinting at the board. If it's the case, oh my god. Okay. If it's the case that okay, so if you're not enrolled in the class, I need you to vacate your seat because I got students who are currently enrolled and need to sit down. Otherwise, there just aren't enough chairs in here. All right. I'll see what I can do with the front office. All right. Anyway. Thank you. I got totally derailed here. Oh, if I write something on the board and you don't understand what I wrote, just tell me that you don't understand what I wrote on the board because sometimes I get excited about stuff and I write too fast. Please, yeah, sit. I guess the other thing is remember that like I am going to be posting. Oh, I forgot to tell the last class about this. So I'm actually using the OneNote, the classroom OneNote here. I've got full sets of the lecture notes I'll be like reading off of. Posted to the Canvas page. You can get onto through the class OneNote. You can just get on these. I think you can actually copy them over into your own folders and annotate them if you want. They'll typically be posted the night before. This is also being recorded, so it's going to be online, so you can go on YouTube later and look at this if you've missed anything, especially at the beginning of the class as people are crushed in or in the edges in here. Right. So anyway, yeah. So what we're going to be doing is calculus in lots of variables in the correct way. So structurally, before I start talking about the math, structurally, the way that I've got this class set up right now is I think 20% of your grade in this class is going to be built on the homework. That's not totally set in stone yet. It may be higher than that. But I really want the homework and the work on these exercises is a big part of understanding what's going on in here. It's on paper. If you work on a tablet, you're welcome to work on a tablet, but I'm passing these off to a grader, so they need to be printed out on paper when you turn them in, if that's okay. I work on a tablet myself. I find that yeah, it's an extra complication to put a PDF layer, like, you know, the capability of turning stuff into PDF. So physical homework is going to be strongly preferred. If you absolutely cannot print stuff, well, come talk to me outside so we can come up with an arrangement where I can print stuff for you. But I can't do that for many people. So homework is going to be basically a week. I'm going to assign like a week of problems. It will be ahead of where the lecture is typically, and then we'll work over through it. So I think I already have an assignment up for this class. It'll be picked up on Tuesday next week, and my plan is to pick it up on every Tuesday, pass it off to the grader, and then they'll get it back like for the next Tuesday. So we'll just be switching off. That means that it's going to be complicated for me to handle late work. My preference is that normally in a class, I'm not a super hardliner about turning work in late, but because I'm having somebody else grade it this time, I'm going to have to be a little stricter with that. So if you're going to miss stuff, I mean, people miss things for all kinds of like legitimate reasons. So if you're going to not do your homework in on time, just let me know what's going on. Okay. What else do I want to say about this? Right. So basically, that's the deal. We're going to come in here. We're going to talk about mathematics. It's not always going to be blasting away at you for 50 minutes at a time. I'm hoping to do some. This is a computational class. And the best way to get a handle on the exercises is to work on them. So we'll be injecting the class when I can with days maybe where we work on problems together in here in groups instead of just like constantly lecturing. I'm not probably going to do. It's kind of suggests I'm doing flipping here by having these videos, but it's not ever going to be like a formal flip thing, right? Like hopefully you guys have been kept up in the class. So I'll tell you that getting behind in this class is a bad idea. Because I mean, that's of course the case for every math professor of all time always says that. So I'm not saying anything new, but this material really does build directly on itself. And if you wait for 2 weeks to try to catch up, you're going to miss 2 weeks of like, it's going to be hard to do that. The other thing I want to point out in this class that's really important for you to be responsible for is this class is going to reveal anything that you didn't learn that you were supposed to in your previous calculus classes. Right? That's going to happen. And if there's a hole and you don't know and you get some idea on the board and you have absolutely no idea what to do, you have to talk to me so I can do. You got to talk to me so I understand, so I know what's going on, so I can either post supplemental material or I can point you to where you're supposed to be. There's not enough time in the class where I can go back and re-lecture huge pieces of calculus 2, calculus 3, calculus 4, but all of those courses are going to be used in here. Okay? So if you're uncomfortable with something, and it does happen where sometimes people just have literally not been taught stuff before, you hit an idea, you don't have any idea what's going on, come talk to me. Don't come talk to me 3 weeks later when you're drowning, right? Early is better than later. Okay. Right, so I'm wearing a mask. This is not supposed to be an invitation to you guys. I probably wear it for the first week because I really cannot afford to be sick. And there's 40-something people that are in this room right now. My understanding from like following on Reddit is basically everyone went to Mexico and got sick over spring break. And I really cannot afford to catch like some sort of horrible stomach flu or something that's going to lay me up for 2 weeks because there's not enough people to cover and it's going to be brutal. So I'm just waiting to see what happens for the first week of classes. You know, that's actually my primary concern. You guys go to Mexico. Come on. They should have been doing math all break. 7 straight days of getting ready for this class. Just get in there. Okay. Let me also point out that I know that the textbook that I assigned for this class is expensive. I should point out that a Google search for the textbook of this class is productive. That's all I'll say about that. What else do I want to say about that? Yeah, so the book in this is built. This book is, it's not a super, you're gonna benefit from reading the book and reading it in a specific way. So this book kind of plays around with trying to be a proof-based book, or it includes a proof-based part of this course, which we are not emphasizing. So when you read the book, you should be reading it for the concepts and the examples. And if you want to go beyond this class in some sort of theoretical way, the proofs are there for you to walk through, but I can't talk about that in the class, right? This is not a proof-based course. The proofs are there. Some of them are very interesting and useful. If you want to talk about those, I would be happy to, but in my office hours, not necessarily in the lecture itself, okay? So don't get bogged down or intimidated if you start reading the book and you realize that she spends the back half of the chapter with 4-page proofs of the main theorem, okay? That's not, you're not obligated to read that stuff, even if it's interesting. But, you know, nerds that like reading mathematical proofs for a living, like, you know, the guy up here in front of the classroom. Okay, so structural questions about the class I can answer before we go on to talk a little bit about what the deal with the math in here is. Yep.
Do you have any general calculus for calculus?
I can, so one thing I can do for that is I can basically post my, I would be happy to post all of the stuff I posted from my reviews for calculus 2 and 3. I haven't taught calc 1 here, but I also have a full set. I have full materials and a full set of videos for both calc 2 and calc 3 up on YouTube, as well as all of my exams and stuff like that. So I can hide that in a module on Canvas if you want to go through it. And then just this is, so I'm going to use you just as an example here. As specific ideas come up, if you need help with specific ideas, let me know so I can focus like some sort of material on those ideas. Okay. Okay. Anything else? Yep. So this class, I don't have, this is the first time I've taught this class here, so I don't have videos for this class. But I'm not keeping, so like, so your question though, I'm not formally tracking attendance in here. You're required to be here, but I'm not formally tracking it. There's not going to be a huge delay typically between when I'm done with these videos and when they go up. I process them immediately after the class is over, and as soon as I get home, typically sometime before that evening, they'll go up. I know that's obnoxious if, you know, I haven't done it today because it's the first day, but I almost always, because I'm using Zoom to record these before I post them to YouTube, I will just put my link to my personal room that I'm recording them in. So these will be available in real time as well. So if you're out for whatever reason and you want to be in the Zoom, you can see this in real time. Now, it's not a hybrid class where I can't guarantee that you'll be able to interact with me, right? But if you have to be gone or you're sick and you just want to see it in real time instead of having to wait till the evening, you can drop into this video and watch it. Okay. And I'm trying, I expect it's still going to be the case that a bunch of people are in and out over the course of the quarter. Right? I would hope that, that it's not going to be overwhelming like it was in the winter. Wash your hands. Anyway, anything other structural questions? Okay. All right. So what is the deal with so if we're done with structure, the last thing I'll say here is that I guess the last structural thing is right now I'm looking at Monday and Wednesday from 11 to 12 for office hours, but I'm going to put up a poll so that people can punch in when they're available. It is not humanly possible for me to hit times that everybody is in a classroom that has 35 people in it. I will do the best I can. I will try to offer diverse slots as well. If it turns out that whatever I decide, the 3 or 4 hours that I put up don't hit you in any way, let me know so I can try to move things around, right? But that's another thing I hate to find out about 6 weeks into the class. Okay. Anyway, my office hours tend to be well attended, and I think they're useful. I don't hide them at like 7 o'clock in the morning or 6 o'clock at night. So please come talk to me in office hours and to help keep up. I also have a Slack channel for the class that I'll be answering questions in. I tend to get to those pretty quickly unless I'm actively teaching. So if you're working on something and you need a hint or you want to talk to each other, last quarter, I taught calculus 3 and of the 8 or 10 students, I have 70 students in the class, and the 10 or 15 students in the class that were on Slack basically all got A's. So I'm not promising that getting on the Slack channel is going to get you an A, but that level of engagement with the material and that support to be able to get it immediately from each other and from me, I think really helps, right? So you don't have to, I'm not grading it, but if you want something to do that's more asynchronous than having to come to office hours or like, and it goes along with when you work on your homework, you should jump in and ask questions, right? I watch it. Yeah, so yeah, just engage with the course. Okay, so why 304? That's a good question. And I'll say it. The answer is that 241 is kind of lame. right? And the reason 241 is kind of lame is because Stewart, the guy who wrote the book, I mean, he's dead, but the guy who's writing the book that has Stewart's name on it, is not very good about using the language of vectors to talk about stuff. He kind of crushes in all of this math in chapter 16, where it just moves way too fast, but also not fast enough. And he's not using the right notation. And almost none of your teachers will have gotten to, just I'm going to say some words that you're supposed to be familiar with. You're supposed to have seen things like Stokes' theorem, and Green's theorem, and Gauss's theorem, the generalized Stokes theorem. You're supposed to have seen these things. And not a lot of professors get there with any time to give it the treatment it deserves. That's the first thing. The second thing is there's stuff he just leaves out that's super important, both for mathematicians and for working scientists, engineers. Things like, what does a Taylor polynomial look like if you've got a function of more than one variable? You're working with a vector function and you want a Taylor approximation for it. How do you even do that? He doesn't do that at all. This is not there. It's one of the most important ideas in vector calculus, and he just doesn't do it. So 304 sort of fills, there's one thing it does is it fills in all the stuff that 241 leaves out. One thing. Then that's two, it actually does the stuff 241 does better than 241. What's 241? Multivariable calculus, calculus 4. The math 241 is one of the prerequisites for this class. That is calculus 4 is multivariable calculus. Okay, so Math 41 sort of does a real shallow treatment of a lot of these ideas, and it doesn't do it in the language of vectors. That's the next thing we're going to do is we're going to use modern vector ideas. I know this is shocking, but if we use vector ideas to do vector calculus, it works better. Vector calculus. Now, the last idea of 304, which is less about like the material and more about like encouraging growth as students of mathematics and mathematical ideas, is for a lot of people, 304 is where you get your first, it's a first real introduction into the way that working mathematicians and scientists think about math, right? It's more relaxed. In some ways, it's more relaxed than the sort of nuts and bolts approach that you see in like a calculus 1, but it's also more abstract, and so it's harder, right? And with abstraction, like this is a hard thing. This class is hard, not because the material is hard necessarily. Well, people have a hard time with this class sometimes because you go from very concrete ideas to ideas that are slightly more abstract than that. And that's a really like hard move mathematically to go from things that are really concrete to things that are broader. Okay. Now there's no proof-based. There's a lot of these upper division math classes have prerequisites that are proof courses. There's no proof prerequisite for this class, but it's still at the point in your mathematical education where it's going to expect you to think slightly abstractly, okay? Even if we're not doing formal arguments. Okay. So the other big prerequisite here, and the language that we're going to be using to do this, is we are going to be using the language of linear algebra. Because vectors describe the functions, but if I want to do things to the functions, I have to use linear algebra to do that. If I'm working with vectors, I should use linear algebra to study them. So this class also has Math 206, which is sort of linear algebra 1. For those of you that have not taken it here, this is basically the language of matrices, right? Linear algebra 1, Math 206, is basically the study of matrices. So things that will come up in here, we'll go over them as they come up. We're going to talk about things like eigenvalues and eigenvectors will be present in this class. Okay, and the description of like functions that take vectors of inputs and outputs that can be described with matrices. This idea of a linear transformation that will also be in here. Okay, so there are going to be ideas from linear algebra you're going to be expected to know. So, for example, everybody, like what we're going to start with today is I'm just going to quickly race through the sort of like the vector stuff from chapter 1, right? It's not going to be like, I'm not just going to like completely blow this stuff off, but I'm going to try to do chapter 1 of the textbook. Is supposed to be reviewed. Chapter 1 of this textbook is about vectors. It's basically that sort of chapter at the end of calculus 2 and the beginning of calculus 3, where you do dot product, cross product, the idea of vector projection. All of that stuff is sort of preliminary work to what we're going to do in here. And that's what I want to talk about today. Okay. Okay, so why multivariable calculus at all? Easiest possible answer to that question is, if you're a math student, because why should I restrain myself to one variable when I have n variables to work with, right? Things are more interesting in n variables. So for a math student, say a pure math student, more dimensions, more interesting. More dimensions, more interesting. For a scientist or an engineer, it's an unfortunate fact that the world is three-dimensional, so you're sort of stuck. If you want to use calculus of an object moving around in free space, there's nothing else you can do. You have to have calculus for objects that move in free space, right? Like a particle moving through an electric field in a particle accelerator is moving in free space with some sort of path that's described in three-dimensional space. And if I can't do calculus on that path, I can't do things like describe how quickly it's turning, what the acceleration the particle is feeling on that path, right? I can't compute things like energy. So for scientists and engineers, the idea is the world is, at least as far as we know, no string theorist arguing with me here. The world is 3D. It doesn't get to be 4D until you go past this class. So it's just a 3D world. Time doesn't exist. And then, not to leave anybody out, if there's anybody in here from computer science, or anybody I've missed between math students, scientists, and I'm sort of as a blanket term for lots of physics and chemistry and all the other majors that end up in here. If there's anybody here in computer science, arrays are vectors. So if you want to do any sort of sophisticated computation with arrays, you're sort of trapped. Okay. Now, you don't necessarily walk around doing calculus to your arrays if you're a science student, but the idea of treating things like vectors and computing with them is an important idea. If you have more specific applications that you'd like to see as we go, I can usually come up with something. So just ask. If you guys an idea and you want to know how it applies to your field as we're going through the class. Okay, so those of you that were in the previous class are going to see a completely different definition in here. So let's start with a review. So we're going to move to actual mathematical content now. So this is a review of vectors. And this is Kali chapter 1. So a lot of these ideas will be things that you've seen before. I'm not trying to insult everybody, but like the background people come into this class with is really wide. People are all over the place with, it's been years since they've done math, or it's not been years since they've done math, or there's pieces missing. So I'm going to try to make sure that we all starting on the same page here. So for us, we are not going to be dealing with abstract vectors in this class. We're going to be dealing mostly with vectors in R3 and vectors in R2 as well. So for us, we're going to think about vectors as being things that look like A, B. And R3 are vectors that look like A, B, C. Two-dimensional and three-dimensional lists of points. Okay, I guess more typically in here, just to keep the notation consistent with Kali's notation. Sometimes they may be distinct, sometimes they may be subscripted, but the idea is that we're dealing with, oh, if you've never seen the symbol before, this just means that is an R with an extra stick next to it. It just means the real numbers, right? So this is two-dimensional real numbers and three-dimensional real numbers. Okay, so vectors have basic operations that they can do. So R2, R3 are what are called vector spaces, which we're not going to go into detail about, but the idea is that you can add them. And you can scalar multiply them. Let me add again. If I'm doing any, this is about as nuts and bolts as we get. As I go through these sort of introductory vector topics, if you see something you've never seen before, let me know. Okay. Scalar multiplication just means that you can take a number outside and multiply it in. 800,000 times in your life, you've seen this definition probably at this point. Okay, so let's move on to Kali now, moving you out of stuff that you've seen before and into her notation for some ideas that show up constantly in physical applications and in what's called analytic geometry. So Kali's going to say, if you have a point P1, and you have a point P2, and say P1 has coordinates x1, x2, and x3. And P2 has coordinates y1, y2, and y3. So there's a vector that connects those 2 points. How do I get it? I subtract. Now, subtraction, the idea that there's a vector that connects these, that's called the displacement vector. And you get it by subtract. If you want the arrow to point from P1 to P2, you subtract these from these, end minus origin. Y1 minus x1, y2 minus x2, y3 minus x3. But she's going to give this a name. The name that she calls this is the vector that starts from P1 to P2. Initial point, ending point. So she's going to be very clear about what the vectors is that she's referring to. This is already an improvement on Stewart's notation, I think. Okay. So that vector, the vector P1, P2, is the displacement vector between 2 points. In this way of thinking about this, where even though we're in R3, we're going to abstractly think about them all as just vectors in R2. That's going to be typical in this class. I'm not going to try often to draw crazy three-dimensional shapes for abstract ideas. I'm just going to write down an arrow. This is how mathematicians do this, right? And also future mathematicians, like everyone in here. Okay, so with this language, with the idea that P1, P2 is the displacement vector from P1 to P2, we're going to define lines, then we're going to talk about the vector products, and we're going to talk about planes. So these are core ideas that we learned for the first time in Calculus 3, and then sort of kind of not in the sort of multivariable calculus. And so hopefully it's not completely foreign territory. The equation of a line, lines in R3. I'm writing these in R3, but the same formulas also work in R2. Okay, so I'm going to write lines in R3. So what is a line? Think of a line as a point, and then another point, and the line that runs between them, right? So a line is the locus of points. It's the flat locus of points that connects 2 lines in the plane. Don't write that down. What do we need to make a line, really? Well, we need a starting point to get us where we're supposed to be. And then we need a vector that points in the right direction to describe where we should go from that starting point, right? To make a line, we need somewhere to get us to where we're supposed to be. and then another vector that points the direction that we're supposed to be traveling. You can think about this as sort of like being the slope of the line. It's the direction the line is supposed to take. If you locate me in space at a point, you then have to tell me which direction to head to get the rest of the line. And that's enough to determine the entire line. I can go backwards on the line just by multiplying by negative numbers, right? Lines go in both directions from a point. So I need a location, starting location, and I need some kind of direction vector. This is where the beauty of this notation starts to show up. She's going to call the origin O, 0. Her equation of a line looks like this. R of t is equal to the vector that connects 0 to P1. That's this vector. So that's our starting position, plus a way to move around on the line by multiplying by some scalar t times this direction vector that I needed. P1, P2. Make sense? So this is the sort of abstract. What's that OP1? That is the line that connects the vector that connects the origin to P1. Yeah, so O here is the origin. So it's not a 0, it's O in the center coordinate. And we're just making, we know it's a vector because I'm putting the half on top. Yep.
Why is it 1?
It's supposed to be this is supposed to, I'm mixing on page now. P0, P0, P1. There. Sorry, my bad. Origin to the first point, which is P0, and then the vector from P0 to P1. I could have labeled it P1. Now, as is what we're going to see over and over again in this class is that things are really elegant if we stick to vector notation. This is a really nice way of writing the equation of a line. But now I'm going to muddy it up by putting coordinates into it. So everybody hates, you should hate coordinates. Like, oh my God, they're going to make you do math now, right? Like I have to throw away this beautiful abstract formulation of a line and actually put numbers into it. Okay, so let's draw the same picture. Or not draw the same picture, but let's actually give names to these things. Let's say P0 has coordinates A1, A2, A3. And let's say that P1 has coordinates B1, 2, and B3. So whatever they happen to be, you can think about this as being located at A1, A2, A3, and B1, B2, B3. If I label things like that, I can get what's called, so this is called the vector equation of a line. It's beautiful, abstract. And then I'm going to muddy it up by writing the parametric equation of a line. Parametric equation. If you make this substitution into this equation, what you get is this. R of t is equal to, oh, hurting my soul to do this. I don't even want to. A1, A2, A3 plus T times B1 minus A1, B2 minus A2, B3 minus A3. Oh God, we computed something. That's the vector that connects the origin to the point P0. A1 minus 0 is A1, A2 minus 0 is A2, A3 minus 0 is A3. This is the vector that connected P0 to P1 with those coordinates. If you expand that out, you get this. Those are called the parametric equations. That lets us break the study of the line out of vectors into the study of the individual coordinates. Okay, so the point here is this emphasizes the coordinates x, y, and z, and this emphasizes the vectors themselves. So this is called the parametric equations. Okay, so parametric equations give us a way of describing what's happening to the individual coordinates inside. Okay, if there's anybody fresh out of their, I guess you can be fresh out of 143. Does anybody remember what the other form of a line is? X plus b. That's y equals mx plus b works only in two variables. This will simplify to that if you just have this. If you just had this, you can solve for t and cut the t out of the equations, and you'll get y equals mx plus b. But the same idea can be used in three variables. Get the t out, right? Because the t emphasizes the fact that there's some particle traveling in space. Is there some? You said something. It's not polar. Oh, don't worry. There's plenty of polar stuff coming in this class. Oh, that's coming too. No, so this is the idea here is the same as the idea if we wanted y equals mx plus b, right? Y equals mx plus b describes the shape of a line by looking at the relationship between x and y, but without having the t in the picture, right? It's saying, what is the path doing instead of what is the particle traveling to make the path doing? So these are called the symmetric equations. And they're basically the three-dimensional version of y equals mx plus b. So x minus b1 over a1 is equal to y minus b2 over a2, which is equal to z minus b3 over a3. So any points x, y, and z that satisfy all three of those equations at the same time are on the line. And if you think about it for a second, this will turn into y equals mx plus b if there were only two of them. So this is sort of like a point slope form for lines in three dimensions. And the virtue here is there's no t. Okay. That's not supposed to say not. No parameters. So we're going to be using all three of these to kind of remind you that they exist. The homework exercises for this first section are going to ask you to go back and do some basic computations. This is the language we'll be doing calculus with. Okay, questions on this stuff. This is what lines look like in vectors. Hopefully this is just a refresher, even if it's a refresher from long ago in the past. Okay, now, cool thing about vectors is that there's multiple ways to define a product on vectors. So the next thing you're supposed to remember is vector products. Some of this stuff will be probably tedious review. Some of it may be stuff you have never seen before. I don't know. So the first product we need to remember is the scalar product, which is usually called the dot product. The dot product is defined as A dot B is equal to this works in 2 and 3 dimensions, but I'm going to define it in 3. This is A1 B1 plus A2 B2 plus A3 B. Right. All right, now a challenge question here. That's how you do the dot product. What is a dot product? Yep. That's a pretty sophisticated way of thinking about it. Yes, that is one way of doing it. Is there another way? So projection. The dot product is a way of thinking about projection, which I'm going to talk about in a minute here. Other ways of thinking about the dot product is. Yep.
And have to do something with or like checking if they're perfect.
Yes, or the dot product also encodes a notion of angle. So you can check if two vectors are perpendicular to each other using the dot product. And yeah, so the dot product is 0, vectors are orthogonal to each other, which means at right angles. So the dot product also encodes a notion of angle. Is there any other way to think about dot products? We got projection, we got angle.
How similar they are.
That's encoded in the idea of projection. Yeah, the closer dot product is the original vector, the more similar they are. But there's one other thing here that we need to know about the dot product. Okay. That's good. I got both of those are excellent answers. Okay. So let's write some properties of the dot product down. The first is, and the one that I also want you to add to the pile is, it turns out that the length of a vector that's the expression for the magnitude of a vector, right? You take the square of the components and you add them up, and then you take the square root. So because of that, because this is the way the length of a vector is defined, it's not hard to see that if you square that, you just get the dot product of A with itself. So the dot product also contains information about the magnitude of vectors. The dot product is really like fascinatingly powerful tool. So the length, this means length or magnitude. Does anybody remember the formula for the angle involved in the dot product? I'd be really impressed. Yeah.
Like length of A and
Yes. All right. Okay.
Wait, sorry, each of those are components, or each of those are vectors.
This is a vector with coordinates A1, A2, A3. So let me do an example real quick here. All right.
So it goes from the origin.
Okay, that's an excellent question. Okay, so when you think of a vector, there's multiple ways of thinking about it, but the standard way of thinking about what a vector is a picture. It's like this, right? The standard way about thinking about a vector is it's the arrow that starts at the origin and goes up here with coordinates of the end has coordinates A1, A2, and A3. There's other ways of thinking about it, but this is the standard way of doing it. Okay? I mean, in the background, vectors are still translation and variant, but when I think of a vector, this is what I think of. Okay? And no matter what this, remember that in a vector, this may answer the question if people have a question here. Vectors measure displacements. They tell you how far you go from a starting point. Vectors tell you how far to move. They don't tell you where to end. They tell you if you started here, how far would you travel to get to the end? Okay. Vectors measure displacement. That's the difference. A point tells you where you are, and a vector says what direction you should travel. Okay. So to compute the length of a vector, if you wanted to compute the length of a vector, I don't know, about you had A was equal to 1, 2, 1. The length of A is, it's like using the distance formula, right? 1 squared plus 2 squared plus 1 squared, which is square root of 4. Don't do that. 1 plus 4 plus 1 is 6. All right, so there you go. That's the length of the vector. It's root 6 long. Root 6 what? I don't know. We're not physicists. Just root 6. Okay. So now let's check and see what A dotted with itself is. Because I'm telling you that like the length of A squared is A dot A. Well, A dotted with itself is 1, 2, 1 dotted with 1, 2, 1, which is 1 times 1 plus 2 times 2 plus 1 times 1 is 6. Oh, look. A dot A is the length of the vector squared. Okay, now let's deal with this. Maybe one of the most important ideas, at least well understood among sort of early students of linear algebra and vectors, is the idea of vector projections. So let's imagine for a second that we had a vector A. Then we have a vector B starting at the same point. A question that comes up in a lot of applications. In fact, every single time in your life you've written a free body diagram and decomposed a force into a gravitational force and a normal force, you've been doing this in the background. Usually not in this language, but this is what you're doing. What you do is you draw a perpendicular line from this vector up to this arrow. You make a right triangle. This vector here, imagine you, again, from the free body perspective, what you've done here is you've taken this force and you're figuring out how much of this force points in this direction. Okay. This is the usual place where you see these god-awful ramp problems where you have a box being pulled with 30 newtons of force at a ramp of angle 30 degrees. You got to figure out how much force is being directed up the ramp, so how much friction is being applied. Yeah, that's this. Okay, this vector is really special. It's called the projection. All right. Okay. I asked this question in this class too at some point. I gave you the short version is, why on earth do they insist on manufacturing chalk at the length of its own resonance frequency? Keep that in your mind. This is the projection of B onto A. So this vector right here is called the projection of B onto A. It takes B and says how much of it points in the direction of A. And has a name, which is, unsurprisingly, the projection of B onto A. That's proj B onto A. So the A is on bottom because that's what's being projected onto. This dude is usually called, I don't know, I guess I won't say usually. If you've seen it before, you've seen it in Stewart. This is called, he likes to use the notation orth. So the idea here is that if you do the projection and then you do this orthogonal vector, then you end up getting the original vector back again. Okay. And the beautiful thing is these have really nice computational formulas, super nice. The length of the projection of B onto A is equal to A dot B over the length of A. That's called the scalar projection. You may have seen that in class before. That's the length of the projection vector. The projection vector, like this. You take that length and you multiply it by this vector. The projection of B onto A is how long that vector needs to be times what's called a unit vector in the same direction as A. If I take the vector A and I divide by its length, the length of the resulting vector is 1. So it's called a unit vector. A over the length of A, or 1 over the length of A times the vector A. Either way, you're taking the vector A, keeping the direction, but throwing away the length. The idea here is that this object, the unit vector, shows up all the time. All it's tracking is direction. That's it. All right, what else do we have? Oh my God, cross products. Yep. Why do I do what? Okay, so what's really, that's a really good question. So what's really going on in the projection formulas, we're going to be doing a lot of projecting here. So it's, if you've never really understood the projection formula or what's going on in the past, it's worth taking the time to try to get it in your head, right? The basic idea is, all I'm interested in the behavior of is B, right? I want B to be left alone, but I don't care how long A is. I only care the direction A points, right? So what I'm going to do is I'm going to take B and I'm going to take its dot product with the unit vector pointed in the direction of A, right? That says leave B alone, figure out how much of B points in the direction of A, but not involving the magnitude of A. Then, however long B has to be pointed in that direction, multiply it by a unit vector in that direction. This is a number that represents a length. This is a vector that only has a direction. So the idea is this shows up twice because you're taking two unit vectors pointing in the direction of A and the steps of the computation. Now, normally the way you guys learn this, and the way I learned it was like this: A dot B over A dot A times A, which I think is completely mysterious what's going on here. Or A dot B over the length of A squared A, which is even more mysterious. Like this formula doesn't mean anything. This is the geometry of what's going on. If you're saying, leave B alone, figure out how much of it points in the direction of A, and then point it in that direction. Okay. I find it much easier to remember the formula like this. Okay. So we have basically some the ideas that we have left to cover. I mean, there's a lot of stuff from vector calculus to cover, right? Like not even vector calculus. What I'm interested in doing now again is this is going fast, not because this is the pace of the entire class, but because this is supposed to be review of vectors. And a lot of professors actually would make you do this on your own, I think. And I'm not interested in doing that. I'm going to tell you kind of what the lay of the land is. So next time what we're going to do is we're going to talk about the cross product, its interpretations as area and volume. And then we'll talk about equations of planes because we're going to be approximating things with planes in this class using calculus. So instead of tangent lines, we'll be using tangent planes in a lot of places. And then we'll be ready to get into like what function theory looks like in several variables. All right, thanks for putting up with this review. It won't be like this the rest of the quarter. See you guys tomorrow.